Hello, my name is Itzayana, and I'm going to tell you about the master thesis with name Effect of Post-Deposition Thermal Annealing on the Optoelectronic Properties of Bismuth Sulfide. The films fabricate via single-step solution processing. Uh, The metal chalcogenides group 6 and 5, in particular, such as bismuth sulfide and antimony sulfide, have attracted significant interest for multiple applications, including photovoltaics, photocatalysis, and photodetectors. In this work, bismuth sulfide thin films were fabricated via spin coating employing a molecular precursor ink with bismuth nitrate and urea serving as the bismuth and sulfur sources, respectively. The effects of the post-deposition, annealing temperatures, and annealing ambient sulfur versus sulfur deficient on the structural, morphological, optical, and electronic properties of the films were investigated. The bismuth sulfide films were evaluated for its use in photodetector applications. Key performance parameters such as responsivity, specific detectivity, and response time are the reported here. The methodology used in this study, bismuth sulfide fins were fabricated via spin coating employing a molecular precursor ink with bismuth nitrate and urea serving. The first used nitrate bismuth was dissolved in 3 milliliters of N dimethyl formamide, and the mixture was stirred at room temperature. Later, urea was added, which is the sulfur source, and the solution was stirred for 60 minutes until a clear yellowish solution was obtained. The deposition of the films via spin coating involved one dispensing 100 microliters of molecular precursor ink on the substrates, two spinning and 2000 revolve for minutes for 30 seconds for uniform coverage. And finally, the samples were subject to thermal treatment in a continuous flow um, tube furnace to induce crystallization. Annealing was performed at temperatures ranging from 150 degrees Celsius to 300 degrees Celsius in 50 degrees Celsius increments under two different atmospheres, pure nitrogen and a mixed nitrogen plus sulfur every moment. The results one structural analysis in the figure A shows the X-ray diffraction for patterns of bismuth sulfide thin films above the as deposit, and after annealing and temperatures ranging from 150 degrees Celsius to 300 degrees Celsius in a nitrogen atmosphere and nitrogen plus sulfur atmosphere. All the fractals uh, exhibit characteristic peaks corresponding to autoromic phase of sulfur bismuth sulfide, sorry, corresponding to the planes 31 310, 220, and 211 indicates good crystallinity even in the absence of thermal treatment. For thermal annealing in nitrogen does not significantly alter the phase of crystalliny on the films, and the figure C and D confirming the retention of the autonomic structure. The bismuth sulfide demonstrated for Raman spectroscopy. Eh, mm, in two cases, characteristics bands produce report for of the rhombic. The bands at 188 centimeters and 237 centimeters are attributed to transverse stretching vibrations. Azimuth of bismuth sulfur bonds. The band at 263 centimeters is associated with the longitudinal vibrational mode B1G, also related to the bismuth sulfur framework vibrations. Raman spectra also didn't any significant change due to annealing temperature of ambient. The morphologi- morphological studies um, presents the surface view and cross-sectional SEMS images of bismuth sulfide in films annealed 150 degrees Celsius and 30 and 300 degrees Celsius in pure pure nitrogen and B nitrogen plus sulfur. The alone ambient reveals a compact and uniform surface with minimal voids on the other hand, annealing in nitrogen mass plus ambient resulted in porous film. See the low magnification images. The the cross-sectional same images. Films annealed at 250 degrees Celsius under nitrogen atmosphere exhibit an approximate thickness of 180 nanometers, which remains largely consistent across different annealing temperatures and ambient conditions. Under nitrogen plus sulfur atmosphere, the corresponding image reveal denser and more compact film morphology. In contrast, particularly for films annealing to and at 215 degrees Celsius, in nitrogen shows a more pronounced root-like structure. 3. Optical and electric analysis analyzes a, C. The variation of band gap, um, B. Urbach energy of annealing temperatures under nitrogen and nitrogen plus sulfur. The optical band gaps of bismuth sulfide samples annealing in nitrogen range from 1.6 to 1.4 electron volts. As temperature increases, while those annealed in nitrogen plus sulfur range from 1.5 to 1.62 electron volts. Annealing under nitrogen only atmosphere resulted in the a decrease of the band gap, whereas annealing in nitrogen plus sulfur atmosphere led to increase in the band gap with annealing temperature. This is according to the literature. The band gap values is influenced by factors such as stoichiometry, crystallinity, and morphology. For the both sets of samples, the crystallinity and morphology were very similar. Therefore, the observed variation in band gap can be attributed to different stoichiometry. The electrical analysis eh, shows A and B figures show the direct conductivity of bismuth sulfide in films annealing and the temperature range from 150 degrees Celsius and 300 degrees Celsius in nitrogen and nitrogen plus sulfur atmosphere. The electrical conductivity of the samples annealing in both atmospheres was found to increase with annealing temperature. The initial improve- improvement in the conductivity could be due to the complete removal of the solvent DMF from the films. The samples annealed in nitrogen plus sulfur atmosphere exhibit higher electrical conductivity compared to those annealed in nitrogen. The dark conductivity on the samples annealed 2050 degrees Celsius and nitrogen plus sulfur atmospheres were are one for 14 5 ohms per centimeter, respectively, indicating an order or magnitude increase in conductivity for the samples annealing nitrogen plus sulfur. Shows the photosensitivity of the samples annealed at different temperatures in both nitrogen and nitrogen plus sulfur atmospheres was observed for difference in both cases with increase in the temperature. The photosensitivity of annealing films increased with temperature up to a certain point, regardless, re- regardless of the annealing atmospheres, and then decreased at higher temperatures. Notably, the films annealed in nitrogen only atmospheres exhibit superior photosensitivity. Maximum photosensitivity of 828 was achieved for bismuth sulfide sample annealed at 2050 degrees Celsius in nitrogen atmosphere, highlight, highlighting its potential for photodetector applications. And 5. The photodetector properties show an photoresponse of bismuth sulfide thin films photodetector in the figure A. See maximum current under dark and illuminated conditions and different applied by bias voltage. B. The current voltage curves measured under dark and illumination and at light power density of 11 milliwatts centimeter for 2, and C. Photocurrent response under intermittent dark light conditions measured and different illumination power densities. The photocurrent as a function of light power density, and the rise in decay time on the bismuth sulfide photodetector and illumination intensity. 11.95 milliwatts meter square rise and decay times and function of power densities. The variation on the annealing temperatures and the atmosphere resulted in significant changes in the stoichiometry and the band gap, while the autoromics crystalline structure remaining stable. The annealing temperatures increment from the 150 degrees Celsius to 350 degrees Celsius under nitrogen atmosphere, resulting in a loss of sulfur revealed by the EDS analysis and the decrement of the band gap causing sulfur vacancies. The device demonstrates stable photocurrent under varying illumination intensities with a rise time of 55 milliseconds, decay time of 90 milliseconds, and a detectivity of 1.2 per 1011 joules under low illumination conditions, highlight its potential for photodetector applications. Um, uh, Going to um, acknowledge acknowledgements. This work is part of the project uh, IN 11 12 45, 44 and has collaboration with the project Puppet in collecting and the RAM and data sharing some chemicals authors that thanks Dr. Enoe Barrios, José Campos, María Luisa Ramón García, Dr. Patricia Altúzar, Rogelio, Elvira, and Gilgardo Casarrubias for collaborate my work. Thank you.